Hello everyone. In the previous lecture, we have discussed discrete random variable. In this lecture, we will discuss the continuous random variable and cumulative distribution function and probability density function of continuous random variable. Continuous random variable can take any value in an interval. Can take any value in an interval. This continuous random variable is used to model the physical characteristics such as time, length, etc. The example of this continuous random variable is the infinite resolution of roulette wheel. An example of continuous random variable is the infinite resolution of a roulette wheel, which can take any value in an interval 0, 1 as a result of spinning of the wheel. The wheel is spun, it can take any value in an interval between 0, 1 and it is an infinite resolution random variable. So we call it as a continuous random variable. We will see the characteristics of the PDF and CDF of CRD, probability density function and cumulative distribution function of a continuous random variable. The first characteristics or a feature is we use the two equations that is used before. The equations are d by dx fx of x will be greater than 0 and fx of x is equal to d by dx of fx of x. From these two equations, we can write that fx of x will be greater than or equal to 0. That is, the probability density function will be greater than or equal to 0. Second one, if x is equal to minus infinity, then the CDF will be 0. The cumulative distribution function will be 0 if x is equal to minus infinity. If x is equal to plus infinity, then fx of x is equal to minus infinity to infinity fx of x dx is equal to 1. Fx of x dx is equal to 1. Next feature, fourth feature is we will again use the two equations we have already discussed it before. Those equations are, so okay, I'll write it as from this here also. From, we can write fx of x dx is equal to minus infinity to s fx of u du, and if a pair of random variables are used, that is x1 and x2 is used, then fx of x2 minus fx of x1 is equal to probability of a random variable will be less than the x1 minus probability of a random variable a will be less than or equal to x2. this will be greater than 0. We have seen these equations. So from these two equations we can write f x of x2 minus f x of x1 is equal to x1 to x2 fx of x dx. That is, it varies from x1 to x2. Limits vary from x1 to x2. If a pair of random variables x1 and x2 is considered, then the PDF will be this, the probability density function. So from this we can write an approximation that if the probability is taken from x less than x plus delta x, then this will be equal to x2 x plus delta x fx of x dx. Now from this, if delta x tends to 0, if this delta x tends to 0, then this can be written as x to x fx of x dx equal to 0. The cumulative distribution function, if it is limit is from x to x. Next, exponential distribution. A continuous random variable CRV can take an exponential distribution if its PDF, that is probability density function, is of the form lambda to e power minus lambda x. For x greater than or equal to 0, and for 0 if x is less than 0. Otherwise we can write it as otherwise also. A continuous random variable can take an exponential distribution if its PDF is of the form lambda e power minus lambda x. This is a random variable. We will solve an example now on a continuous random variable. Example is the phase of the sinusoidal carrier. How to model the phase of the sinusoidal carrier. In AM system. Found between plus or minus pi radians. Now, we can write it like this. The probability density function y, as it is a probability density function, we'll write it f y of y here, and so as it is a continuous random variable, it will be in some interval. So we'll take a phase here in an interval between y1 and y2, and this will be equal to 1 by y2 minus y1. This is the PDF, the probability density function, and we can write this as f y of y is equal to 1 by y2 minus y1 for y between y1 to y2, and 0 otherwise. Now we will find the cumulative distribution of this, the CDF of this. The CDF of this uniform random variable, if it is from, we know that if the CDF from minus infinity to infinity, f y of y will be equal to 1. From the previous equations we discussed it before, we can write like this: minus infinity to infinity, the cumulative distribution function will be equal to 1. Now, if it varies from y1 to y2, f y of y is equal to, f y of y is this 1 by y2 minus y1, y1 to y2 1 divided by y2 minus y1 dy. When we integrate this, we will get 1 by y2 minus y1, as it is a constant. We will get y here, and we integrate 1, and the limit will be from y1 to y2. Now upper limit minus lower limit, we will get y2 minus y1 divided by y2 minus y1. It is y2 divided by y2 by y2 minus y1 minus y1 divided by y2 minus y1. I have written directly y2 minus y1 divided by y2 minus y1. It gets cancelled and it will be equal to 1. That is the cumulative distribution function from y1 to y2. Next, we have to make a note of this. From y1 to y2, the CDF is 1. From y1 to y2, the CDF is 1. If the probability is y greater than or equal to y2, y after this greater than or equal to y2, we can write it as y1 to y2 fy of y dy plus y2 to y f of y dy. So this is a perfect enough. y2 to y, it is 0. y2 to y here, PDF is 0. You can write this as 0. From the previous example, from the previous equations, we solved that y1 to y2 it is 1. 1 plus 0. So equal to 1. y1 to y2 is 1. y2 to y, this is 0. Write it 0 as it is. Okay. So for y greater than y2 it is 1. Next, for y1 to y2, we have seen the equation that f y of y will be equal to minus infinity to x fx of u du from the previous equation. This is the previous equation. We will apply it here. So this can be written as f y of y is equal to, here it is x, here it is y. So we can write, and here it is from minus infinity, but here the interval is given, that is y1. y1 to y. Here it is given minus infinity to x, here it is y, and minus infinity is y1 here. It is not minus infinity, it becomes y1 because interval is given here. It becomes y1 to y, 1 divided by y2 minus y1. Integrate this, you will get y1 to y into 1 by y2 minus y1. So this upper limit minus lower limit, it becomes y minus y1 divided by y2 minus y1. For y greater than y2, it is 1. For y greater than y2, this part, y greater than y2, it is 1. For y1 to y2, it is y minus y1 divided by y2 minus y1. For y less than y1, it will be 0. As it is a 0 here, for y less than y1, it will be 0. Now we will draw the cumulative distribution function for this. So we will summarize first whatever we got. F y of y is equal to, it is 1 for y greater than equal to y2 after this, and it is y minus y1 divided by y2 minus y1 for y1 to y2, and it is 0 for y less than y1. So the cumulative distribution for function is let us take the same interval y1 and y2. For y greater than y2 it is 1, means we will mark somewhere 1 here. Y greater than y2 after this, so it is 1. It is 1, y greater than y2. Next, y less than y1 it is 0. Less than y1 it is 0 on this. Next, y from y1 to y2 it is y minus y1 divided by y2 minus y1. That is, we will join this. So this is the CDF, cumulative distribution function. Anyhow, if I integrate the unit step function, I'll get the ramp function. Thank you.